Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to the Electrical Engineering channel. In this lecture, I will demonstrate modified Maxwell's equations for time varying fields. And time varying fields means if the field expression, either the electric field or the magnetic field, if the expression of these fields contain the time derivative term, then that field is called as time varying fields. If there is no time derivative term in these electric field expressions, then these fields are called as static or steady fields. So let's first discuss Faraday's law, and we all know that according to Faraday's law, induced EMF is proportional to the rate of change of magnetic flux, and EMF is equal to minus d phi by dt mathematically. The negative sign actually corresponds to the Lenz's law, and we also know that induced EMF is equal to E dot dl closed line integral. So if we have a time varying field, then E dot dl closed line integral will not be equal to 0, and for static fields, E dot dl closed line integral will be equal to 0. So it means that um, d phi by dt is the time varying magnetic flux linking the closed path. So this is the derivative of the magnetic flux, and E dot dl is equal to minus d phi by dt. And we also know that phi is the magnetic flux, which can be written as the surface integral of B dot ds. So we can write B dot ds in place of phi in this expression. So E dot dl will be equal to minus d by dt phi, and it will be equal to minus partial b over partial t dot ds. And we also know that if we apply Stokes' theorem on this expression, E dot dl line integral will be equal to del cross E dot ds surface integral. And we can compare these two expressions, this one and this one. So minus partial b over partial d dot ds is equal to del cross E dot ds. It means del cross E is equal to minus partial b over partial t. So this is the modified form of second Maxwell's equation. Uh, and for steady or static fields, the curl of electric field was equal to 0, but for time varying field, del cross E is equal to minus partial b over partial t. This is a modified Maxwell's equation in point form, and the integral form of this Maxwell's equation will also be discussed later. Now we can write Ampere's law in time varying fields. So we know that according to the point form of Ampere's law, del cross H is equal to J. And let's evaluate the dot product of vector operator on both sides. So del cross H will be equal to del dot J, and del cross H will be equal to 0. So if we take the divergence of curl of any vector field, it will always be equal to 0. So this is the property of the vector operator. So it means this term is equal to 0, but this term del dot j is not equal to 0. So when we derived the expression of the continuity of current in fifth chapter of the textbook, we came to know that divergence of volume current density is equal to minus partial rho v over partial t. So del dot j is equal to this expression, but the left hand side is equal to 0. It means for time varying fields, when we have the time variation of the charge, this expression of the point form of Ampere's law will no longer hold. So let's assume that del cross H is equal to J plus G. So this is our assumption, and G is an unknown vector field. Now apply this dot product of vector operator on both sides. Then we will have del cross H equal to del dot J plus del dot G. Okay, so dot product on both sides will give us this expression, and this expression is equal to 0. This is equal to minus partial rho v over partial t plus del dot G. So del dot G will be equal to partial rho v over partial t, and we know that rho v is equal to del dot D. This is the point form of Gauss's law, and del dot G can be written as partial over partial T rho V and partial over partial T del dot D. So this thing can be written as del dot G equal to del dot partial D over partial T. So this divergence or del dot term can be taken out. Now we can compare these two sides and we will get G equal to partial D over partial T. So this value of G can be substituted in the original expression, this one. So del cross H is equal to J plus partial D over partial T. And this is the modified form of Maxwell's third equation in point form. And this will hold if we have time varying fields. And H dot dl is equal to I plus partial d over partial t dot ds. This is the integral form of Maxwell's third equation or integral form of Ampere's law in for time varying fields, and this is the point form of Ampere's law for the time varying field. Similarly, this is the point form of uh, Maxwell's second equation for time varying fields, and this is the point form of Maxwell's second equation for time varying fields. Okay, so E dot dl is equal to minus partial b over partial d dot ds. And we can summarize all these four Maxwell's equations for time varying fields. And you can see that this is the first equation, second, third, and fourth. First and fourth equation will be same for steady and the time varying fields, but the second and third Maxwell's equations, they will be modified and for time varying fields. Now, if we assume that these are static fields, then B will be constant and D will also be constant, and their derivatives will be equal to zero, and we will get again the Maxwell's equations for static fields which we obtained previously. So from these set of Maxwell's equations, we can observe that time varying magnetic field is producing electric field, and time varying electric field, okay, so this is electric field, time varying electric field is producing magnetic field. So this is the property of electromagnetic waves. So electromagnetic waves actually have a magnetic field, time varying magnetic field along one axis, and time varying electric field along the other axis, and they are actually orthogonal fields in electromagnetic waves, the electric and magnetic fields. And the propagation or direction of propagation of the electromagnetic waves is perpendicular to the both electric and magnetic fields. So time varying electric and magnetic fields actually causes the electromagnetic waves to propagate in the medium. So that is all about our today's lecture on time varying Maxwell's equations for time varying fields. And I hope you have understood the concepts of Maxwell's equations for time varying fields and the principle of electromagnetic waves. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.